Um, I'd really like to introduce our speaker today, Ankur Desai. Ankur works for the University of Wisconsin-Madison. We're talking a little bit about climate change and what we might be able to do to help with that. So without further ado, I'd like to bring Ankur to the stage and hand it over to him. So Ankur, go ahead and take it
All
away.
right, thank you very much. And I'm going to start my screen share here. And we'll assume that's moving forward. But yeah, thanks Andy for having me come present today. And I'm happy to chat and hopefully save some time at the end for any questions you have. The topic that we were asked to talk today is a little bit about how do we collectively together address the challenge of climate change around the globe. And I'll share a little bit about my work, but to understand that, we need to understand what we're talking about. And so here's so this picture here is a solar field where we're doing some research, and I'm gonna save that one for a little bit later to talk about what we're exactly doing at, but just as a teaser. But I want to start with something a little bit more newsworthy, which is that here's a picture of a village in Switzerland that was recently completely flattened by a glacier that collapsed. And this was on May 28th. This is a photo from the Associated Press, and we can actually look at this not just from the photo, but also from space. So here's the NASA OLI imager on the Landsat satellite. And so here's the village Blatten, which is in the Alps and clearly surrounded by these glaciers. And notice this one that says Birch Glacier. And this is the image before and previous year. And if we look at just immediately after the glacial collapse, you can see the effect of the flooding on the glacier like that. Now, that's a recent extreme event that happened in the news. And you might wonder, if you're thinking about something like that, could we have improved warnings about something like this in advance? Thankfully, in this case, there was actually warnings a few days in advance and nobody was harmed, although lots and lots of damage to property occurred as this. And you might wonder, well, does this have something to do with our warming climate? Did this make this event happen more likely in terms of the increased warmer temperatures causing the glacier to recede? And could we decrease the harm from events like this and help communities be safer? Those are the types of questions that my lab at the University of Wisconsin, which we call the Ecometeorology Lab, focuses on. And here's a picture a few years back of several of our students and researchers that come from everywhere from India and China to New York and California and Indonesia and Germany and Minnesota and Wisconsin. We focus, and here we are at Mickey's Dairy Bar in Madison, and the questions that my students and staff really like to think about are exactly what those questions were from before. How do we use science to better understand the effects of a climate change on ecosystems, on society, on people? And how do we take advantage of some of that understanding to improve our ability to make safer communities, as well as to have innovations in technology that allow us to potentially prevent future harms? And that's also the type of work that's done by the people in my department, which is the Atmospheric and Oceanic Sciences Department here at the University of Wisconsin-Madison. So here's a picture of our very tall building that you might have seen if you're in Madison, because it's pretty visible from a lot of angles. We have about 20 faculty who work on all sorts of questions about weather and climate. We're one of the largest departments in the country in terms of training future meteorologists and climate scientists. And we also work in close concert with two units in our building, the Space Science and Engineering Center, which is a home of researchers who, about 70 years ago, invented the very first weather satellite and launched that to space in the late 1950s. And the Center for Climatic Research, which pioneered lots of efforts in understanding past climates through a variety of paleoclimate proxies, as we call them. So think of things like tree rings and corals and things like that. And the combination of those satellites and that past climate record is actually how we understand things like glaciers, as we saw a few slides ago. So, for example, here's a nice image where you combine past records along with satellite data from the last 50 years. And one of the things we can see very clearly is this decrease in annual change in glacier mass, which is accelerating in its loss through the last few decades. Now, there were periods in the past where we did have glacial loss and glacial gain, but what we see is from about 1970 onward. And that's the kind of data that we collect as scientists collectively through investments in satellites, in major scientific expeditions and studies to better understand how the world is changing and how we might be able to understand what causes it and how we could maybe help protect society from it. Of course, I can't give a talk today as a climate scientist in the United States without bringing out the fact that all of this, as you just saw, is at major risk of loss. We are seeing dramatic cutbacks in the funding for federal science in the US. And most of that funding goes to supporting the scientists and the people and the students you saw a few slides ago, as well as those measurements and expeditions to better understand the science. The cuts that are being proposed would nearly cut our scientific investment in the US by more than a half, bringing us back to 40, 50 years ago in terms of science funding, despite the massively increased needs. That said, I don't want to make this a downer talk, but we will be undeterred. So here, for example, is all of the NASA Earth observing and planetary satellites that will be canceled next year if the budget passes as is, including that Landsat satellite, which is where the image from those glacial loss estimates came from. But we'll be undeterred because we've been through things before. We've been able to understand and how to use creatively science to better understand problems in whatever environment we're in. And more importantly, the people, right? So the vast majority of scientific funding goes to supporting people, and science is made of people. These are climate scientists. This is what climate scientists look like. Here's Alan, a master's student with me who came from UW Whitewater, who's trying to improve forest management in northern Wisconsin using new NASA satellites. Here's Jir Bai, who, after some significant challenges in being able to get into the US, joined my lab this year as a visiting researcher from China, trying to improve agricultural water management. Or Jonathan, a UW-Madison economics student who's better trying to understand resources of ecosystems. Emily, who you'll hear more about her work later on, she's from Seattle and she's interested in renewable energy. Susie, who came from Germany and was a postdoc in my lab, who created a whole new way of understanding greenhouse gas emissions from farms. Or Anthony, who grew up in Puerto Rico and has a fascination with extreme weather and studied South American hailstorms and how we could better forecast the risk of catastrophic hail damage. Or Srinath, who came from India and is now a professor at Texas A&M studying turbulence and fluid. Or Bethany, who is a postdoc who studies agriculture. Or Jordan, who came from Jackson State in Mississippi, who wants to understand urban heat islands in his hometown of Atlanta. Or Bailey from Alaska, who grew up in the northern ecosystems of high latitudes and is interested in how forests are changing. Or Kieran from India and onward. Or Jen from Milwaukee. Science is made of people who have passions, desires, and life stories and an interest to solve puzzles, to get to the bottom of ideas. And sometimes those ideas challenge our understanding, and sometimes they impact policy or lead to new technology, and sometimes they change the world. And these are the people that I try to support and protect as they continue their work as climate scientists. All of their salaries are funded by federal grants that are currently at risk. But they will be undeterred because they fall on a legacy of people who were undeterred. Climate scientists is built on a history of individuals spending enormous amounts of time often against prevailing conventional wisdom about how to understand the world. So Eunice Foote, for example, in the 1850s was one of the first people to experimentally demonstrate the link of carbon dioxide to warming. However, she was prevented from presenting her work on account of being a woman at the time. We have other people who, Joseph Tyndall or Svante Arrhenius, who made some of the first estimates of how much the world would warm from fossil fuel emissions, despite having very little observational evidence and a lot of questions about how reliable that science was, until folks like George Callender came about and made careful measurements to show that the climate indeed was warming even in 1938 from industrial revolution fossil fuel emissions. Or Gilbert Plass, who put together some of the first theories of how the oceans and the atmosphere work together. Or Joanne Simpson, another early leader in our field who was fascinated by tropical storms and really wanted to understand hurricanes and convections and how they involve in the climate system, despite also facing a lot of roadblocks and being able to advance her career at NASA. But all of these people, including my students and all of these, had a singular interest in understanding the atmosphere. So here's a beautiful picture from the NASA International Space Station of Earth at night. And what I'm most interested in here is that very thin layer of little light that you're seeing, the sunlight being reflected off the atmosphere. The atmosphere is relatively thin compared to the Earth as whole, and yet it sustains all life as we know it. And it is this atmosphere and its myriad physics and chemistry and biology, along with its connections to the ocean and the land, that is what drives all of these people to want to do the work they do. And a lot of times that work has dramatic impacts on being able to protect lives and property. So here's a great image I like to show. Here's this Sherry Rowland and Mario Molina, both of whom later on went to win the Nobel Prize in chemistry. But here they are in the 1970s trying to sort out what is going on with the atmosphere, in particular with a series of gases, and what was driving the loss of what we call stratospheric ozone, which is protecting Earth's surface from ultraviolet radiation that's harmful to biology. And what we had learned that through the 1970s, the use of chlorofluorocarbons was leading to a dramatic decrease in that ozone, particularly over Antarctica. And it led to thousands of scientists trying a whole bunch of different hypotheses until we really nailed down the impact of chlorofluorocarbons. And we were able to use NASA satellites and other types of imaging and data and experiments to really understand that by the 1980s, we were seeing a dramatic loss in stratospheric ozone, which took 7 years later, in 1987, the development of the Montreal Protocol to reduce CFCs and eventually lead to the healing and recovery of the ozone layer and preventing millions or possibly tens of millions of premature malignant skin cancer deaths in humans. And the same story is going to be happening for climate change, even if it takes a little bit longer, because as much as there's a lot of news and negative things as we see about extreme events and so forth, it's not too late. And especially if we work together, there is no stopping, regardless of what we're seeing on happening in any one country about its science funding or about politics and onward. So to help all of you get a little bit on the same page as I am about how we understand climate, we're going to do a little bit of climate change 101. And the short story here is it's happening, it's us, and it's harmful. And most importantly, we are learning more every day on how to reduce that harm through science, through technology, through policy, and through a shared common purpose. Now, I can't give an entire course's worth of climate science here in our hour that we have. And I do encourage those of you who are in Madison or else, that UW, for example, offers some great climate change intro classes, including in my own department, Atmospheric Science 102. But there are also lots of great resources online on YouTube. Folks like Catherine Hayhoe and others who have created some great YouTube channels on climate science, and I encourage you to check those out if you want to go deeper. So let me give you kind of the 10,000 foot view of here. So first of all, what is climate? Climate is not anything much more fancier than the average of weather, right? So weather is what we experience every day, temperature, pressure, humidity, precipitation, and climate is just the average of that over some space and some time. So you might think of the average climate of Wisconsin over the 1980s, right? So some sort of spatial area and some sort of time domain. Typically, we think in the order of decades and we think in the scale of entire regions to continents to the globe, right? And I like these quotes: climate is what you expect, weather is what you get. We believe it was a meteorologist in the late 19th century who kind of said this first. So a lot of people say Mark Twain said it, but that seems to be a little bit of a myth. And this one, my colleague Marshall Shepard, who's a scientist as well as a contributor to Forbes magazine. And he writes, climate is your personality, right? Your background, right? Whereas weather is your mood in any one day. So those are some ways to think a little bit about climate versus weather. And we can look at climate. For example, here is climate over the last century in Milwaukee, right? And the blues here are cooler than average years relative to 1960 to 2010, and the reds are warmer than average years. And what you see is that the frequency of warmer years relative to cooler years increases from about 2000 onward. But there are some interesting periods in the 1940s and 50s, related to, as well as you might be able to see a couple of other years sticking out, some particularly cold years in the late 19th century. But if you start taking all that data, it's kind of like, well, I don't know if that's global warming or not. But that's because we're not looking at the whole world at once. And global warming is really about what we see when we put everything together. So now if we take all of that same data from all sorts of places in the world, from tens of thousands of data points, and we work out all of the various considerations of how to make good measurements, we start to see a pattern that emerges of a particularly startling pattern that happens from about 1970 onward, but really starts around the 1930s or so, with the with the start of the acceleration of the Industrial Revolution and the post-World War II economy developing from the 1950s. As I like to tell my undergraduate students, most of whom are now born after 2003, they have never experienced a below average year in terms of global climate. And that warming marches on. So this is a group from Berkeley Earth using an independent estimate of global temperatures, and they kind of come to a very similar conclusion. And in fact, what they see here is that 2024 was continuing what we're seeing in 2023 and 2025 up till April is kind of on track to be somewhere similar to that. And this climate change is unusual in that for the past 10,000 years since the last glaciers receded from this part of the world, we've had a relatively consistent climate, which has allowed agriculture and human civilization to grow and flourish. There have been fluctuations, and you might have heard about some of these, like the Little Ice Age or medieval warm period. But once the Industrial Revolution took off, we really see this upturn in climate that is putting us outside the bounds of anything that humans have lived in ever, right? And then the question is where we're headed are places that the world hasn't seen in maybe millions of years. Now, how do we know this is driven by humans? Well, one thing we have to do is connect it to what might be changing on the planet. So we know, for example, if we compare 1970 to 2020, that the emissions of fossil fuels has nearly quadrupled from about 10 billion tons of carbon dioxide per year to almost 40. And why we care about carbon dioxide is because it is the primary driver of what we call the greenhouse effect. So this is a graph of a bunch of numbers on it. Don't worry too much about the numbers, but focus on kind of the big arrows, right? So basically, our planet is heated by the sun, like all planets are heated by stars. And that amount of energy that we get from the sun is absorbed primarily by the surface of the Earth. The atmosphere doesn't really absorb a lot of sunlight. That's why we can see the sun in the air. But as that atmosphere, as the Earth heats up, it releases infrared radiation. That infrared radiation then is added back to the atmosphere. Now, if we didn't have an atmosphere, Earth itself would be completely frozen over. It would have an average temperature of about 0 Fahrenheit, which is maybe not an unusual temperature for January in Wisconsin, but not the true temperature of our planet as we know it. The atmosphere does something pretty dramatic, which is it acts kind of like a blanket in that the presence of gases like carbon dioxide and water vapor and methane and others are very effective at absorbing infrared radiation that's emitted from Earth's surface and decreasing the amount that is emitted back to space. And by doing that, some of that energy then is then emitted to the Earth, which is then providing more energy to allow the surface of the Earth to be warmer than it would be otherwise. And that kind of cycle or loop is called the greenhouse effect. And as we add more greenhouse gases, we increase the amount of energy that is being added to Earth's surface, and that increases its temperature until we reach a new temperature as a function of the amount of carbon dioxide and other gases in the atmosphere. Keep this image in your mind because we'll come back to it in a second because there's an important point here. This is known as the energy budget of the Earth. But basically, the amount of temperature of the Earth is equal to energy in minus energy out. Now, how do we know it's fossil fuels that's driving carbon dioxide? Well, one, we directly measure how much fossil fuels are being emitted. And so I didn't cherry pick 1970 and 2020. We can see a steady increase in fossil fuel emissions. Yeah, there's some economic recessions and there's oil crises and there's the pandemic that sets us back now and then. But there's been a steady march and increase in fossil fuel emissions since through the 20th and into the 21st century. And that can be directly linked to the increase of carbon dioxide. Carbon dioxide has a lifetime of hundreds of years in the atmosphere, and therefore the increase in CO2 can be directly linked to fossil fuels. Now, you might say, did I also cherry pick these two numbers here, 1970 and 2020, where we've seen CO2 increase from 300 parts per every million parts of atmospheric molecules, which are mostly oxygen and nitrogen, to 400? And the answer is no, because I measure this stuff in my own lab. So here's a site in northern Wisconsin where I work with my partners at NOAA currently. And inside this funny looking shipping container is a bunch of analyzers that are what we call infrared gas analyzers. So because carbon dioxide can absorb infrared radiation, that's what drives the greenhouse effect, we can also shine infrared light on carbon dioxide that we sample from the air in an analyzer and directly and very precisely measure the amount of CO2 in it. And I can do that every hour. And I've been doing that for about 25 years and sharing that data with NOAA as part of their global CO2 record. And what we see is that there's all sorts of interesting patterns that I don't have time to go into. I'll just kind of hint there is this kind of interesting seasonal cycle. That's actually the breathing of the biosphere. That's photosynthesis, taking up CO2 every year and growing trees and plants and everything else. But what's important is this steady rise in CO2. And this isn't just unique to my one site in northern Wisconsin, but if you take all of the sites around the globe where NOAA collects this data and put it together, they tell exactly the same story. And that's because CO2 is long-lived and it mixes around the globe relatively efficiently. And we can directly link that to fossil fuels. So here's the atmosphere in 1850, and we know how much coal we've used, how much oil we've used, how much gas we've used. We know how much land use change there is. And if that was all that was happening, we'd actually have CO2 much higher than we have in the atmosphere. But because we have photosynthesis and the regrowth of forests and some fertilization and longer growing seasons, and we have the oceans taking up some of that carbon dioxide, CO2 is not growing as fast as our emissions, but it is growing. And that global growth rate, that year to year change, which is what this graph shows from NOAA, is actually been increasing with time. In fact, last year set a record in their growth rate of CO2. Now, remember, you might say, well, okay, fine, CO2 is increasing, but how do we know that's actually changing the greenhouse effect? Because what about all those other greenhouse gases you talked about? And that's kind of a neat thing. We can use other satellites in space, completely independent measurements, and we can measure that change in how much sunlight is coming into the Earth and how much long wave radiation is being lost to space. And that actually has been increasing, right? So that's an energy imbalance. And this paper published just last month basically shows that that imbalance has more than doubled in recent decades. The imbalance is the sign of the greenhouse effect. This means that Earth's temperature has to warm to be able to go back into balance. And that is what's going to happen over the next century. This isn't new science either. And in fact, there's this very nice review paper by a colleague of mine at Princeton, Suki Manabe, who wrote The Role of the Greenhouse Gas in Climate Change. And Manabe is important because he was the first person to put all these pieces together in a computer-based model. And he did this in 1967. And he basically showed that how, by putting in all of that energy imbalance into a computer model of Earth's atmosphere, you can simulate and very accurately predict the greenhouse effect on local surface temperatures. Now, you may not be super convinced by this, but Manabe also made another important prediction, which is that well, if you increase greenhouse gases, it's not like you created new energy. What you're doing is you're warming the surface, but that energy has to kind of be traded off somewhere else. And so as we increase CO2 from 150 to 300 to 600 ppm in this experiment, the surface warms, but the stratosphere, the upper atmosphere, this y-axis here is the height in the atmosphere in units of altitude or pressure, decreases unlike any other thing. So if it was the sun that was heating climate, both of these things should warm. If it was the oceans, we would see the oceans warm first and then the atmosphere. And so this is a strong hypothesis, right? That if it is the greenhouse effect from fossil fuel emissions from CO2, the surface should warm and the stratosphere should cool. And in fact, we now have observations to show that that's the case. And not surprisingly, this work led to the Nobel Prize in Physics for Manabe in 2021 and is the basis for all of the climate modeling we do today. So here's this really cool figure from a paper that came out just last month. So on the top is temperature in the atmosphere with time and height. And on the bottom is temperature in the ocean with depth and then again with time. As we can see, there's a couple of things. We can look at the lower atmosphere and we can see very clearly that the surface is cooler and then it warms with time, just like we saw before. But notice what's happening in the upper atmosphere. It's actually going from warming to cooling, exactly as you would predict from a greenhouse effect theory of a warming climate. Moreover, notice what's happening in the oceans. A little bit more subtle, but notice how the surface is warming and the oceans are warming too, but they are kind of lagged. So then the surface ocean warms, then the deeper ocean warms. And that's also a sign that this is a greenhouse effect warming because the surface is warming first and that heat is being transferred into the ocean. So we now have nearly unequivocal, and the reason we say we have nearly 100% consensus on what drives climate change is because of very careful work and measurements like this that have led to the theories. And not surprisingly, it's allowed us to have federal government reports that say things like the continued release of CO2 from fossil fuels will almost certainly cause significant changes and be deleterious for humans, not controllable through local efforts. What may surprise you is that this statement was already well known in 1966, right? This is Lyndon Johnson's Science Advisory Committee. And all that we've been doing since then is improving our models to make better predictions and to make better understanding of what's happening around the world. So here, for example, are a whole variety of different computer models. Here's Manabe's initial model, which actually underestimated the actual climate change that happened in black. But many, many other models got improved with time. And through the 70s and the 80s, they got more and more accurate at being able to predict global climate warming. And you can see here that our best models today can even capture some of these smaller scale changes due to things like volcanoes and El Nino and other things you might have heard of. Further, it's not just the models in theory alone. There are thousands of papers by thousands of independent climate scientists that have looked at everything from ancient climate records in coral and trees to theoretical models in physics to other climate records and like things like lake ice and everything else to modern observations that all basically settle on this fact that doubling CO2 will lead to something like a 3 to 4 degrees Celsius or a 5 to 7 degrees Fahrenheit warming of climate. The thing we can do in the models is then play games and say, okay, well, what happens if we reduce greenhouse gases or increase greenhouse gases? How do we separate the effect of greenhouse gases from air pollution, like aerosols, which mostly cool climate, or land use change or natural causes? Climate is changing because of natural causes and because of greenhouse gases. And it's collectively the effect of the two that's driving the change we see, driven mostly and primarily by greenhouse gases. And the reason we talk a lot about this right now is that we're at an inflection point in our climate record. We are at a point now where dramatic impacts on what we do in the future of fossil fuels is going to have a dramatic impact on the next 100 years of climate. And so the decisions we make in the next 10 to 20 years is going to set us on a course where we may have a relatively modest amount of climate change that we could probably adapt to and address the harms with some level of better warning and better technology, or areas where things might be very unsustainable and lead to dramatic conflict and migration and other issues that will be difficult to manage or have significant costs on the global economy and societal well-being. And another way to look at it is this way. So you might be, well, what's the big deal about a few degrees? And so here is a nice article that was actually in the New York Times a while ago. And it's basically showing all of the summer temperatures in record highs and lows across the United States from 1950 to 1980. And if you know your statistics, you know that this is known as a Gaussian or bell curve. And what you can do is compare it to that climate change from 2005 to 2015. And that small change in about like a half a degree temperature increase in Celsius is not the real issue. The real issue is what's happening on the edges, right? So now cold extremes are less common and hot extremes become much more common. You've basically loaded the dice. If you know statistics, you may also know something about the fact that this Gaussian distribution went a little bit down. And what that means is that the tails or the edges of our distribution got fatter. And so what this is saying is that from 2000s into the 21st century, the extremes have actually become more common. And we can attribute that to a changing climate. And in fact, that was the other half of the Nobel Prize in Physics in 2021, which was a climate scientist in Germany named Klaus Hasselmann, who came up with a theory of how do we link the changes in climate to the changes in extremes? And how do we link those to action? How do we know that climate change is making an event more likely? And it's his work on climate attribution that allows individuals to look at things like saying the last 500 of the 750 extreme events that we've seen in weather had happened because of climate change, or that climate change made them much more likely to occur around the globe. We can see a similar thing with the way that NOAA collects what's called billion-dollar disasters, a database that was currently went dark because of the federal funding cuts. But basically, what it shows is through a combination of extreme weather events and changes in investments in properties along places with flooding or extreme weather, we're seeing an increase in those events. And we can even drill down to the regional scale. So here's the Wisconsin Initiative on Climate Change Impacts, which is a group that includes the university, private industry, and the government, kind of looking at extreme weather index trends across Wisconsin. And we see some very similar things. with some spatial variability, where we see more increases in southern Wisconsin compared to northern Wisconsin. And what's happening in Wisconsin is somewhat of a more complicated story because the temperature increase, warmer temperatures allow for a faster water cycle, more evaporation, more precipitation, a greater amount of water vapor in the atmosphere. And that's exactly what's driving the extreme weather events here locally, which is that we see in all seasons, winter, spring, summer, and fall, for most of Wisconsin, an increase in precipitation, maybe decreases in northern Wisconsin in the summer. And that's an interesting potential feedback from plants using water faster, using water up faster in the North Woods. But one of the things that drives is that the prediction of days with rainfall of 2 inches or more, which for most urban areas leads to flooding, or at least minor flooding in most regions. And what we see is a prediction from these models that because of the increase in the water cycle, is likely to go from a few days a decade to something like 10 to 20 days a decade, which would significantly stress water systems and flooding management in places like Southwest Wisconsin and Milwaukee. So the question is, what are we going to do about this? Right. And I kind of have this down to three things, right? Because people talk a lot about, oh, well, what do I do in my backyard or my light bulbs? I think there's really three things that individuals need to think about, which is to get educated, to get engaged, and to get empowered. And you're already doing this first step by being here, which is to get educated, to learn a little bit about the science and the technology and the people behind it and why they care about this. And then to think about where in the places that you live and work and engage with society and policy, are there places where things about climate and weather influence policy? And learn about those and advocate for the causes you care about and to get empowered to learn how to make change. Because ultimately, it is about our collective actions and our needs that are going to really help us reduce and replace the fossil fuels that are amazing and have done amazing things for society with the next amazing sources of energy and technology that aren't as harmful to climate and society and ecosystems. And so when we think about these, we have options, right? And there's kind of broadly in the climate solutions community, we talk about two sets of options. One is there's some amount of climate warming that we have to adapt to. There's really no getting around that because even with rapid reductions in fossil fuels, there's some climate warming that's going to happen, some impacts to oceans and sea level and other things that are going to take time to reverse. And some of those things are going to be economic, like paying for damages and sometimes reducing poverty, which helps improves resilience to climate damages. And some of those are going to be technology, like curing diseases that would otherwise be spread by increasing vector-borne mosquitoes, for example, or things like that. And the others are to reduce it. And in the interest of time, we'll just focus on examples. People are already adapting to climate change. We've seen extreme weather events throughout the United States, forest fires. Here's a picture in North Carolina from a few years ago in the Washington Post of individuals raising the level of their homes to protect against increased flooding from tropical storms in the rising sea levels on North Carolina's coast. Those are the kinds of things that we do with adaptation. At some level, though, fundamentally, adaptation can only get you so far. And ultimately, what you have to do is reduce the atmospheric greenhouse gas concentrations back to places that limit the impact of a changing climate. And we do those through a variety of means. Some can be economic, so policy things that make essentially pollution more expensive. We've seen that be relatively successful with things like acid rain and air pollution in the United States and elsewhere. There can be regulatory agreements like fuel standards and so forth, and energy standards, as well as kind of changes to transportation and industry. And there can be societal changes like education or technological changes like capturing of CO2. And the reason we have to think about all of these is that greenhouse gases and carbon dioxide and fossil fuels are in everything we do, right? And fundamentally, to mitigate, society has to reduce that greenhouse gas concentration, and there's no single solution, right? Because every single piece, so electricity is a quarter of our greenhouse gases. Land use and agriculture and food production is another quarter. Transportation is 15%. Industrial uses of energy is 20%. Home heating and cooling is like 6%. So you can't just be like, oh, if everyone just had an electric car, we'll be all better off. Or if everyone used solar, or if everyone used regenerative agriculture, or if everyone switched to heat pumps, right? Because each one of those has a small impact on reducing greenhouse gases. And it's really about the collective impact that matters. And the reality is that that impact has to be relatively large. So this is somewhat of a busy slide, but basically this is showing our total, again, we saw this earlier, which is our total emissions from fossil fuels. And this is where we are right now with global treaties like the Paris Agreement that you might have heard about, which are the nationally determined contributions, or how much we are already committed to reducing fossil fuel emissions, which is not nothing. But if you compare it to what scientists have projected is required to keep climate from warming by more than 2 degrees from 1850, which we're approaching quickly, it requires a relatively rapid reduction by 2050 to our fossil fuel emissions being back to something like the 1970s, despite having about twice as many people in the world. But there are lots of things that do work, and we know. So, for example, this is an older slide, but this showed that, for example, even in the United States, we could cut our emissions in half solely by looking at things like electrical efficiency, passenger vehicle efficiency, a slight increase in the use of renewable energy, and some slight increase in carbon capture. Each one of these alone doesn't solve the problem, but collectively, just these six things alone could essentially lead us to reducing our fossil fuel emissions in half. Now, you might say, wait a minute, what about countries like China and stuff that are rapidly increasing fossil fuel emissions? And you're absolutely right. In fact, in the United States, since about 2000 or so, our fossil fuel emissions have actually been decreasing slightly. Some of that is because we switched from using oil to natural gas, but some of this is also about real changes in efficiency. And China has been rapidly developing. A lot of this is also from a rapid growth of manufacturing of things for the entire globe. But they've also made some dramatic investments, which we'll talk about in a little bit. And moreover, this is where we are today. But if you take the entire long view, remember how I said carbon dioxide can stay in the atmosphere for centuries? Well, we have to go back to the long view and think about, well, who's responsible for emissions all the way back to the start of the Industrial Revolution? And if you look at it from that perspective, while China has been responsible for a lot of emissions in the last few years, the historical obligation of those emissions that are still in the atmosphere go back and lean primarily on the US and Europe. And so, in terms of who needs to reduce emissions, if we want to reduce the harmful effects of climate change, it's really everyone. And really, the developed world has a first obligation while also supporting the rest of the world in the emissions that it may generate in the future to be able to grow its economy and grow and support its population. So I want to just talk about one of those potential climate solutions and then maybe hint on a second one for a little bit of time. So my lab has been looking a lot into the impacts of expanding solar energy. And so as you saw a version of this picture in the very first slide, this is work that our lab has been doing here in Madison, looking at the vegetation and how it responds to expansion of solar energy. And I'll talk about why that matters in a second. But the reason that we want to focus on solar is that solar is now the fastest growing and cheapest source of electricity globally. And you can see here that solar installations have been growing rapidly, and in fact, growing about 3 to 5 times faster than any projection that's made. So every 5 years, world energy agencies make projections, and the projections constantly get beaten by what actually happens on the ground. You can see a lot of that is actually happening in China. China is rapidly decarbonizing, probably one of the fastest in the world. But many other parts of the world, including in the US and North America, are also rapidly increasing in solar because it is cheap. It's cheaper than fossil fuels, and it's a good source of electricity. And we've learned how to deal with issues around storage and intermittency using better battery technology. Places like Texas is one of the world's leaders in solar energy. But when it comes to the Midwest, where we have a lot of land and a lot of potential for solar, we also have a lot of land that's used for agriculture. And the real question is, can we generate and expand solar while not harming all of the benefits and support we have from agriculture? Can we grow food and generate electricity potentially in the same place at the same time? And if we do so, what are some ecosystem impacts? And this has led to a lot of interest in trying to understand what's known as the science of agrivoltaics. Because while large-scale utility installations of solar is where most of our new solar growth is going to come from, even in the Midwest, there's a lot of interest in potentially in medium to smaller scale solar installations on farms that can provide income security for farmers because they can generate money from leasing the energy they produce to power companies, while also still growing crops by changing the spacing of the solar panels and the orientations. And the real question is what crops do well here? What types of grazing do well? And does it maybe even increase production as we've seen in some parts of the Southwest by saving water? And so my lab, along with my colleague here, Steve Lohide, who's in civil engineering, he's a groundwater ecologist and water scientist, have been working at this site in Stoughton with the University of Wisconsin and partnering with Alliant Energy, where you can see some row crops that are just being established here. This is rye in between these solar panels. And we're putting out high-tech instrumentation. This is at my student Emily, who I mentioned earlier from Seattle, who's now doing a PhD around the ecosystem impacts of increasing agrivoltaics in the Midwest. And these towers allow us to directly measure the change in plant productivity and plant water use as we grow crops in between these solar panels. Last year, she mentored Liz, who is a freshman computer science and environmental sciences student at UW-Madison. She grew up on a ranch in Arizona that her parents immigrated to from Mexico, and she had a strong love of land and a strong aptitude for coding and software, and she wanted to combine those two to be able to make the world a better place. And so she worked with us last year to kind of do some pilot studies to really understand how much is productivity different under the panels versus near the panels versus open fields. And we thought the highest productivity would be in the open fields in the control. But in fact, what we found was that the productivity of the plants was highest in the partial shade in between the rows. And part of that was from increased water redirection from the panels, and part of that was from the partial shade reducing evaporation and potentially helping productivity. We don't know yet, and this was a little bit of a surprising finding, but it really shows how complex biology is and really the role that biology plays in understanding climate. And so that's my other thing I want to talk about, which is that, of course, there's been a lot of interest in understanding can we use biology to also help us offset the harmful impacts of climate change? This is just a scanning electron microscope image of a single stomata on a plant. This is where how CO2 comes in and water comes out of a leaf. This is just found on social media, but it was a nice segue to talk about the fact that, of course, you've also heard on the news possibly that there's a lot of interest in how do we enhance the amount of carbon dioxide in the ground? Can we increase carbon sequestration to reduce the amount of CO2 in the atmosphere to what we call carbon dioxide removal or nature-based climate solutions? And so the reason people talk about this is that there is a lot of carbon in the ground, particularly in wetlands, particularly in high latitude forests, and even in the tropics. And there's been some papers that have come out on things like the global restoration potential, that if we went and conserved and restored forests in many parts of the world, we may be able to dramatically increase the amount of carbon stored in the ground, thereby decreasing it in the atmosphere. And there's been lots of large scale efforts. For example, I'm a trustee of the Wisconsin chapter of the Nature Conservancy, and the Nature Conservancy is focused a lot on conserving land. And one of their focus areas lately has been on how does that conservation also help sequester additional greenhouse gases out of the atmosphere. The challenge is where and how much and how long. And so my lab has also been spending a lot of time trying to study what we call the carbon cycle of forests. So here's an image from yesterday at one of the forests I study in northern Michigan, near the Sylvania Wilderness. It is a 300-year-old old growth forest. And what we do in many of these types of forests around the globe is we build these towers. So here's a picture of me with a lot more hair from about 30 years ago, building my first tower at that same forest. And what these towers allowed us to do is to combine, they directly measure the amount of carbon dioxide and photosynthesis going into these forests relative to the amount of decomposition happening on the forest floor. And I can connect that to things like satellites in space from NASA and elsewhere to be able to map that amount of carbon sequestration from things like forest restoration and forest conservation. And we do this in not just our old forests, but also in things like our younger forests or our managed forests, like this one here in northern Wisconsin, in the Schwamigan National Forest. And we can compare how much carbon is going into that kind of very productive forest in the blue year to year. And you can see that's pretty a large bar. That means lots of carbon is going in, compared to my older forest where there's a little bit less, but it's not zero. And I can also build other towers that are even taller and start bringing into wetlands and to pastures and urban landscapes. And I can start to get a more nuanced picture where it's like, well, yeah, some of these forests can take up a lot of carbon, but they aren't the whole story. And to piece all of these together is something my lab has been focusing on to better quantify how much carbon can we actually sequester. Because the reality is, as much as we would love to be able to expand these carbon dioxide removal technologies and ideas by improved forest management and sequestering carbon in soil and elsewhere, they're not going to be the way we solve climate change. They are a solution, but they are a secondary solution. We have to do things like renewable energy and fossil fuel replacement to be able to really decrease fossil fuel emissions. But once we get to a point, we have to use some fossil fuels, right? There's no getting around that. Fossil fuels have some pretty amazing uses that there are no good substitutes for in things like a variety of compounds we produce and elsewhere. And that's where things like carbon dioxide removal, whether that's sequestering it underground or in the ocean or in the forests, or through direct capture in the air and converting them into things like road pavement products and so forth, all need to be studied because they all have variety of pros and cons and risks, but they can only take out a fraction of what we do. The good news is that solutions are abundant and there's lots of them. So here's the Project Drawdown. This is a great resource to really dive deep into all sorts of different things, some that are everything from family planning to refrigerant management and what is the actual contribution to climate change solutions. Because here's the hard part for policy. Part of science is about failing consistently until we find something that sticks. You can't predict in advance which ones scientifically will work until we study them. And that's the hard part for policy, right? Because we want to be able to find a solution and do it, right? But that's the whole game. This is the whole American science innovation model that has been copied the world over, which is built on unfettered freedom to work on ideas about the universe in settings where there isn't pressure to apply a specific train of thought or line of inquiry, but one that where we are heavily scrutinized by our peers at every single stage, from funding to publication. This is the entire model of scientific innovation. It is the basis of things like academic freedom, of tenure, of peer review, and federal grant funding, all of which is currently at risk. But this is how we make progress, and we know how to reduce harm from a changing climate by basically reducing fossil fuel emissions to the atmosphere. More efforts we do, the more innovation we get, the more technology, the more jobs, the more revival of a safe and prosperous society and economy. And you might say, well, there's all these naysayers, right? And what about them? And the reality is that while the media might try to elevate some voices here or there, if you actually survey Americans, what you see is that the vast majority of Americans care about climate change, are concerned about climate change, and those numbers are increasing. And that those who basically say this isn't happening, or I don't trust the science, or I don't want to think about the impacts on ways of life and new technologies and energy is a relatively small and diminishing percentage. Further, if you ask them about very specific policy questions, so this is another group out of Yale University that does surveys every few years, things like renewable energy, tax rebates on energy efficiency, regulating CO2, um, have really strong support, more than people think. And this is where the get educated and get empowered part matters. After this talk, go talk to somebody else about something you learned at this talk and see what they think about it. And then go tell others. And then maybe think about the next time you're at the ballot box or you're thinking about a politician and what their positions are, how they respond and think about these issues, because that's the only way we make change about these types of questions. And the reality is, this is another busy slide, but even things like global treaties, which tend to have a lot of, concern, hey, how do we actually get things to change? What this graph is showing is that even with the current targets that people are making and with current efforts, the Paris Agreement has actually had an impact. Even with the rollbacks of the US in the 2015s and the re-signing on in the 2018s, the Paris Agreement has staved us from the worst impacts of climate change, these 3 to 4 degrees Celsius warmings in the 21st century that would have set us back to tens of millions of years in climate, to something that is maybe 2 degrees, still harmful, but areas where we know how to adapt. And with continued effort, maybe bring us to things like 1.5 degrees of warming, where we can primarily protect and conserve many of the things we take for granted in today's climate and weather. We have ample solutions to address climate change impacts. We just need the will to make them happen. And those range from social science questions in economics and policy, to technology questions in carbon capture and storage, to scientific research on better design and better understanding of predictions of things like large scale engineering of Earth's climate. And how do we get them to scale is a big question we're focusing on in our lab and in other labs. And what is fair to people, to environment, society across the world in terms of who's most vulnerable, who's most impacted, who pays most of the costs. And those are the questions that we need to focus on. And true, there are sometimes inefficiencies in how we do this. Sometimes there's groupthink. Sometimes there's periods of stagnations and challenges in how we communicate. That's for sure. But the way to fix those is not by destroying all of that or attacking all of that. We've been working on making our science fairer and more effective and making real strides and making it impactful for society. And that's what I hope I've demonstrated today in our presentation. And I want to thank you for taking the time for listening. Feel free to ask questions here, but you can also reach out to me on email, on social media, on Blue Sky, and you're welcome to look at more details of some of our research at our website here listed. And I'll leave you with this beautiful picture of a meadow in northern Wisconsin taken from a small aircraft with a colleague of mine. Thank you very much.
Ankur, thank you so much for the contextual evidence and practical ways that we might be able to make some impactful change here. We did have some questions that have come through, and still have some time for additional questions. So be sure to populate those in the chat or the Q&A section. Before we jump into these questions, this did come up. This event is being recorded and will be sent out to the email address in which you used to register for this event today. First question from Stephen. Are there studies that show the effects from animal digestive anaerobic activities and maybe how they impact climate change?
Yeah, absolutely. So the question here is about so some animals, and particularly livestock that we raise, along with other organisms, have digestive systems that use anaerobic, so no oxygen digestion systems that then produce methane. Methane is a relatively potent greenhouse gas because it is in a lower concentration than carbon dioxide in the atmosphere, and it absorbs infrared radiation in wavelengths that are currently mostly emitted to space, so they don't warm climate as much. And so there's a lot of interest in reducing methane emissions because that could allow us to get a very early win in reducing climate change impacts. What we know is particularly cows, and through the methane that they breathe out, that has a major contributor to agricultural greenhouse gas emissions. I wouldn't say it's the dominant, but it's certainly a large one. And there's been a good number of studies showing that even some small changes to feed and diets and dairy practices and livestock raising, you can actually reduce that methane emission, but it is a significant source. I don't have the studies offhand. One of the nice things is every 4 years, Congress mandates the federal administration to produce something called the National Climate Assessment. That is meant to be for the public and policymakers, and it drills down deep into things like what is the agricultural contribution to climate change and so forth. That goes into detail. There's also global reports like the Intergovernmental Panel on Climate Change, and as much as that sounds like an intimidating phrase, they actually write reports meant to be for non-scientific policymaker audiences. And they go deep again into the specific studies that support these points about what is the impact of anaerobic digestion on climate.
Very cool. Very cool. Thank you for that. Follow-up question. In regards to some certain products that might be impacting the climate. Question is, can we ban certain products that are
Mm.
absolutely destroying our climate balance? For instance, plastic manufacturing has what effect on our planet's overheating besides the effect on our health?
Right. Yeah, and I'm not a politician, right, or a political scientist, and so in terms of what is the relative policy benefits of banning products relative to other types of incentives or mechanisms to reduce usage, there's pros and cons to doing something like that. What I can share is the story of chlorofluorocarbons, right? So those are the
Hmm.
primary compounds that were destroying stratospheric ozone and increasing skin cancer risk. Even in that case, right, it wasn't an outright direct ban at first. And the reason for that is that there are some products, but there were no known alternatives. And it took some time to develop alternatives to CFCs were a very nice compound for things like propellants and fire extinguishers and for making insulation products and for styrofoam and things like that. And until there were good alternatives and refrigerants, and until then there was kind of a need to kind of phase that out. And so what they did was they said, let's immediately ban the ones we know that we have good alternatives for, and let's revisit every 4 years in this global treaty, which ones can we continue to kind of ratchet out? Because CFCs is a class of compounds until we get to a point where there's only a few left that are just fundamentally we don't have a good alternative for. And that's how they kind of got to that, to essentially saying
Mhm.
we ban CFCs. Something similar has to happen for these things like plastic products and stuff. Like, yeah, there are side effects, right? How is this used in society? What are the pros and cons of banning something? And the challenge is, of course, that national scale regulation can only impact an individual country, right? And treaties don't have an easy way to ban without having individual countries all agreeing to do something. And the challenge of fossil fuel emissions is that CO2s and methane and everything else is in a lot of different processes.
Mhm.
And so banning a single plastic manufacturing product is going to have a relatively small impact, right? Whereas making some incentives where the cost model is like, oh, this is now becoming more expensive to pollute. I need to start investing in research for alternatives, maybe a smarter pathway. Again, that's a political science question, not as much a physical science question that tends to be the kinds of things we focus on.
Sure. Thank you for your insight in regards to that. Another question here for a non-scientific person committed to helping the climate, I found abundance, quote unquote, to be a helpful roadmap for what
Hmm.
can be done. Do you have any other recommendations for books, articles, or resources? Thank you. I know you gave an example of one that a resource that is kind of written at a non-scientific level, but was wondering if you have any other books, articles, or resources that you might recommend.
Yeah, I mean, there's been a plethora of just, books and video resources from a lot of climate scientists. What I would do is, focus on the ones that are from, those who are climate scientists and researchers in climate, those who work. I mentioned a few resources in my slides. I mentioned Catherine Hayhoe, who has this nice background of both climate sciences and political science, and as well as being a chief scientist at Nature Conservancy and also married to a pastor in the evangelical Christian movement, and so has these very different lenses and perspectives
Mm.
of how to talk about climate to very different communities, whether that's scientists versus politicians versus those who care about stewardship in the earth from maybe a faith-based perspective. So her YouTube channel is Global Weirding, I think is what it's called.
Okay.
And she has a lot of nice short segments that I think do a nice job of explaining some basic ideas. There's been some nice edited volumes focused on understanding climate change from the perspective of scientists. The Heat Will Kill Us First, I think, is one of those. A couple documentaries on that same topic. Those are some good resources I would focus on. And like I said, one of the really nice things about the University of Wisconsin system, right, is that, retirees and folks who are older can take classes basically for free. And we have some introductory climate classes that I've had senior auditors take, and they've very much appreciated some of the things we talk about. I also teach a class called AOS 171 Global Change that goes a little bit deeper into the science and into the policy and technology side as well. Hmm.
Wonderful. Well, thank you for that. That actually concludes all the questions that we've had come through today. Encore, thanks
Fantastic.
so much for
Hmm.
sharing your insights with the audience here today. Lots of really,
Yeah.
tangible takeaways. And again, thank you so much for providing kind of a broader context of the how and the why as it pertains to the climate impacts and resilience. As we kind of conclude here, oh, we got another question actually that just popped in. So, how do we connect with Encore? Are you able to share your slide, the last slide that you had pulled up there,
Yeah, yeah, I can do that real quick here.
contact
Just
information up there?
bring it up right here. So my
Yeah.
email address there, desai@aos.wisc.edu, is probably the best way to contact. I'm a little bit of an email addict, so I actually will get back to you if you email me. And so, but I do post time to time on Blue Sky on social media under Prof. Desai. And occasionally we'll share news insights or repost things about recent climate trends and things like that. And so certainly if you just want a more kind of open kind of and there's a lot of great climate scientists both on Blue Sky and also on LinkedIn, where climate science has kind of decamped from Twitter for various reasons, and so those are the two social media sites that you see most climate scientists on right now. But yeah, feel free to email. I'm happy to. I love questions specific about our research or general climate questions. I do have some resources on my website with links, particularly if they're kind of basic questions or if it's kind of school groups that want to do more interview type questions. But anything specific, especially about our recent work in agrivoltaics or carbon cycle and climate solutions, that's an area that, I've been thinking a lot about and happy to kind of follow up on some of the more details from the talk today.
Super cool. Well, thank you for making yourself accessible and available to the audience. As we kind of conclude here and wrap up this event, we are a community that is built up of fellow fearless dreamers here at DreamBank, and we always like to ask our presenters, Encore, what's one piece of advice you have for someone who is actively pursuing a dream right now?
Yeah, I would say, lean on the people who want to support that dream, right? I feel like, as a scientist, I think a lot about the collaborators and friends and colleagues that built through time, and I wouldn't have been able to do any of my science without the fact that I had other people who gave me support and encouragement and collaboration to make those dreams happen. We don't ever do anything on our own in any stage of our life. And so that is true for even what you're eating to breakfast down to what your dream is down the road.
Wonderful. Thank you so much for that, Encore. And with that, we will go ahead and cap things there, and we will see you all next time. Take care.
Okay, thank you very much.